All right, welcome. So I'm Vikto ria Fro hlich. I'm coming at you from Hungary, from Konkoly Observatory, and I'm actually going to double up on talks right now. So we changed a little bit on the schedule. So I'm going to introduce you to two of our recent papers in our little collaboration. And in the first talk, I would like to talk to you about a pathway to some rogue worlds, which has not been explored in so much detail yet, which is planetary ejection by type 2 supernovae. Right. Okay, so of course I don't really have to introduce you to this slide. We know that starless planets roam the roads of the Milky Way, and now there are hundreds of such rogue planets discovered by different surveys and different groups. However, the two most well-known causes for their ejection basically comes down to these two hypotheses. One is early dynamical instabilities, which we have talked about a lot in today's sessions. This includes, of course, planet scattering or stellar flybys or anything you can think of on a similar scale. And what I would like to talk to you about, which has been touched upon a little bit earlier, is mass loss at the end of a star's life. And in our case, we have been working on specifically with type 2 supernovae for the last couple of years, and we have produced a couple of studies on that. Now, where I'm actually coming from is not the rogue planet side of things, but the bound planet side of things. Already the first ever discovered exoplanet that was discovered in 1992 by Watson and colleagues orbits a pulsar, so a neutron star. And this means that there had to have been a supernova explosion in this system. And yet, as you can see on the little diagram, this neutron star is orbited by 3 planets, which is highly intriguing. Now, there are basically 3 possible formation scenarios in such a system. So we either capture a planet, which in itself is already kind of unlikely, and then capturing of 3 planets is even more unlikely. Or you introduce some kind of second-generation planet formation from basically the fallback material of the supernova, where you would actually have to have a disk formation, which is already questionable. Or the third possible scenario, which we are going to explore, is you can maybe survive a supernova on a stable orbit. And I'm going to show you how this is non-trivial as well. So what we did in our papers is use some numerical simulations to model a star that explodes as a supernova. So the red dot is the star. Orange stuff is the envelope that expands around it. And it's kind of hard to see, but there is in blue a planet that starts out on a tiny non-eccentric orbit, whose orbital elements are going to change in time because the star is going to lose its mass. You can see in the equations we have that m in t, so it depends on time, and it's going to decrease in time. And for this mass loss model, we introduced a homologous envelope expansion model that has not yet been used in the literature, as former studies usually assumed some kind of linear mass loss or an adiabatic mass loss where only your semi-major axis is going to change and it's not going to affect your eccentricity. We ran like 1 million simulations with different initial conditions, going for orbital elements of the planets, and then the masses lost, and also the masses of the remnant neutron stars, and also different ejecta speeds. And we followed up on the orbital elements of the planets. And if the systems became unbound, we also took a look at the peculiar velocity of these components. And so as you can see in this specific simulation, the orbit of the planet widens and also its eccentricity is highly increased. And this opens the opportunity to form some rogue planets as well if the eccentricity goes above 1. Right, so I already mentioned this homologous envelope expansion model. So what this means for us is that we have a planet on a certain orbit that you see on the upper panel, and then the supernova envelope is going to start expanding, and this expansion is going to be homologous because the velocity of each layer is going to be a linear function of distance. However, the outermost layer is actually going to have a velocity that is constant in time and does not change, and then also the density profile of the ejected material is not going to change. So this is what you see on the plot. The density profile stays self-similar through different time points. However, this envelope is going to pass the planet basically in 3 phases. at first you have all of the mass inside the planet's orbit, then there is a constant density core of the envelope, which is not the remnant star, it's just within the envelope you have a core part that's going to reach the planet, and then eventually the outermost envelope that is described by a Power law will also pass by. And then on the bottom, you actually see the mass evolution in time. So at different outermost envelope velocities, called Vmax, you see how this is very not close to linear. And you can also see that, especially at higher velocities that are more typical of type 2 supernovae, this mass loss basically takes place within 100 days or so. So this is just a little summary of the model. We have a supernova progenitor orbited by a planet, or we actually in the paper looked at stellar companions as well, but I do not have time to go into that, and they're a bit off topic. So if you have any questions on that, feel free to ask later, but I will skip on that this time. And so we have basically two outcomes. Either the planet stays on a bound orbit and becomes a pulsar planet, or we just have a lonesome wandering neutron star and a rogue planet. And from our about 1,500,000 simulations, we found that over 90% of these models produce rogue planets and lone neutron stars, and only about 9% produced pulsar planets on bound orbits. So what do those bound orbits look like? On this plot on the top, you see the semi-major axis of the bound planets. In the middle row, it's the post-explosion semi-major axis compared to the pre-explosion semi-major axis. At the bottom, you have the eccentricities. The different colors correspond to how much mass the supernova lost, and the different columns represent the remnant masses. So altogether, you can derive that the semi-major increases at least by twofold. So A is going to double in the supernova explosion, and also A is going to increase the more mass you lose. However, what is interesting and can be kind of seen in this bottom right plot, that eccentricity actually has a chance to decrease in these supernova explosions as well. So it doesn't necessarily go up. Now, in order to have a bound orbit, there are two criteria that you have to meet. One is that your pre-explosion eccentricity has to be at least 0.4, which is very significant. And also you need to have the explosion to happen when your planet is very near the epicenter of its orbit, because that's the most stable point. Now, also interestingly, all of the results that I show you here, and also the results that are regarding the rogue planets, are going to be pretty much independent of planet mass. So we tested everything from Earth mass up to 10 Jupiter masses. And basically there's no difference in between the results from all of those sets. The doubling of the semi-major axis is also going to mean that we can only explain pulsar planets whose orbits are at least 4 AU, because the progenitor stellar radius of these type 2 supernova tends to be at least about 2 AU. And of course, we would exclude planets orbiting within the stellar envelope previous to the explosion. So now on to the main topics of rogue planets. You have seen these plots in inverted colors before, but I'm going to go into a bit more detail right now. On the x-axis is the speed of our rogue planets, and on the y-axis is the speed of the neutron star remnant. And of course, we know that these rogue planets are going to originate then from the lower eccentricity orbits, as the bound criterion was that you would need a very high eccentricity. So rogue planets are more populous from the low eccentricity orbits. And you can see that their velocity can reach as high as 275 kilometers per second. On the left plot, the different colors again correspond to different planetary masses, and you can see that the velocity of the rogue planets is basically independent of their mass. However, on the right-hand side plot, you see different colors marking different true anomaly values, so meaning signaling orbital position. And you can see that the smallest velocities actually come from when the system is at epicenter, and the highest velocities can be reached when the explosion happens at the pericenter. So going a little bit more in detail onto the role of this orbital position, on this big plot you see curves that are on the x-axis you have the true anomaly, and then on the y-axis you have the eccentricity, and then eccentricity equals 1, so the bound-unbound regime is always marked with a horizontal line. The 3 different colors represent 3 different initial semi-major axes. And then on the left, you have a smaller initial eccentricity. On the right, you have a larger initial eccentricity. Top 2 panels are a smaller ejecta velocity. Bottom 2 panels are a larger initial velocity. And you can already see that these curves are a little bit asymmetric. That is because in our models, we calculate the true anomaly at the moment of explosion and not when the ejecta reaches the planet. So in between the 2 events, there is a couple of days, and the planet can move a little bit on its orbit by the time that the supernova ejecta reaches it. This is why you see the asymmetry more profound on the top panels where the ejecta is slow, and then when the ejecta is quick, you basically see the symmetric curve again. Now, on all of these plots, you can see that the bound regime is very, very close to the epicenter of the orbit. So true anomaly equals to pi, in this case, 180 degrees. And you can also see that you get more bound systems as you increase the initial eccentricity. And then now back to our original question, can we explain some of the pulsar planets that we see roaming around? And there's actually one planet discovered by Starova and Rodin in 2017, the telephone number of which you can see on the screen. And we can actually explain this planet if, of course, the eccentricity of the progenitor system was high, and then also if the planet orbited the star on an orbit with a semi-major axis of about 5 AU or less, because right now the system has a semi-major axis of about 10, and you have to account for at least a doubling of the semi-major axis. However, this other bona fide pulsar planet discovered by Watson and Fro, it still is a mystery. As I have told you before, it is highly improbable that there have been many 3 planet captures, and also second generation planet formation from the fallback material is hard to, it needs to be studied in a lot more detail. Also, we would like to study how a 3-planet system works and how the stability can be or cannot be sustained in a 3-planet system. And also, just as in a general case, anything that is closer in than about 2 AU, which is actually most of the pulsar planets, will require some kind of additional mechanism to account for orbital decay. So this was the first part. I will leave up the conclusions, and I think I will go to questions a little bit, and then we can go on to the next set of slides. That's also okay for you.
Any questions?
Thank you. Ethan Sun, University of Toronto. Just by intuition, the kinetic energy imparted to a planet to make it go a couple hundred kilometers per second seems to make it would be comparable to the binding energy of the objects. What are the prospects for the planet to survive the supernova as an object at all before the dynamics are concerned?
Right, very, very good question. I do not have numbers in my mind right now of like exactly how much that binding energy is or what it is compared to that kinetic energy of the supernova, but you are making a very good point, and this is a question that is yet to be answered.
I want to build on the previous question. So Alex Bolchan discovered that planet in 1992, the planetary system, and since then he wasn't able to find any other planets around pulsars, to the extent that in 2008 he canceled the entire search program. So that brings me to the question, but what do you think are the prospects of your planets? And I mean, that's aside from the efficiency and process of the formation. But in general, what do you think the prospect of your planetary systems are?
Right. I mean, even now we have around 8 pulsar planetary systems in total. And even that is kind of debated. It goes from like 5 till 12, the number of those. So we're even not sure in each and every one of them. However, it's not a one-off. So I guess we should pay some attention to it. But also from our models, it just pops out that you have like a couple of percent chance for stability. So they are very hard to make.
Well, within the couple of percent is quite substantial. Yeah. So yeah. Anyhow, thanks so much. Yeah.
Okay, so just for the 3-planet pulsar, the first pulsar planet system, right? It's actually a millisecond pulsar, which means that it had to have accretion, which is most likely all those that we know are probably coming from a binary system. So in the binary system, and that was my suggestion of second generation actually, and not exactly how to discuss it, is it's a companion transfer mass produces a second generation disk and the planets form in that disk. And then the companion itself can be ejected if it by itself exploded, for example. So in this case, you can actually get coplanar planets. Everything is fine. So in principle, and it's also explained why it's a millisecond pulsar. But then that's just a comment.